Okay. Okay. The second topic of chapter 3 is about matrix inverses. We have covered some of the materials in chapter 1, but we will pursue more properties about matrix inverses here. All right. So first of all, we consider general rectangular matrices. So we let A be an M times N matrix, and B, sorry, an N times M matrix, right? So A is M times N. So A has M rows and columns. Sorry. But B has N rows but M columns. Okay, and when A multiplies B, M times N, N times M is equal to the identity matrix of dimension M, then A is called a left inverse of B, and the B is called a right inverse of C. Okay. Right, let's take an example. All right, so we let A to be 2 times 3. So it's a 2 times 3 matrix. Okay, and the B is a 3 times 2 matrix. Okay, so A and B are not square matrices. They are rectangular matrices. Now we multiply these two matrices together. Okay, when we multiply together, we find that it becomes to a 2 by 2 identity matrix. Okay, so okay, but not that. Okay, later on. So we say that. So A is a left inverse of B, because A is in the left hand side of B, and B is a right inverse of A. Okay. So that these two things describe the same situation. Whenever we know B is the right inverse of A, then we know A is the left inverse of B. Okay, so these two statements are equivalent to each other. Okay, so they are equivalent. Yeah, equivalent, and they describe the situation as A multiply B equal to the identity. But if you do the other way, you find that this is not equal to the 3 by 3 identity matrix. Okay, you find this is not true. Okay, and you will see actually that for a rectangular matrix which is not square, you can't have both of them, okay, to be true. Okay, only one, at most one of them to be true. But in many situations, this may not be true and this may not be true. Okay, so but for at least for this example, we know we can have two rectangular matrices such that A times B, A multiplied with B equal to the identity. Okay. All right. So if this happened, then there are something special inside, behind the scenes, and we want to dig out what happened behind the scene. Okay, such that we have this special situation. Okay. All right. So the first theorem. Now, if an M times N matrix A has a left inverse C, okay, so the dimension of C should be N times M, i.e. C is a left inverse. Okay, so if this is the situation occur, then any linear system AX equal to B, B is in M. Okay, so any linear system has at the most one solution. Okay, so that given the information that a matrix A has a left inverse, then when we encounter any such a linear system, B can be any vector in Rm, then this linear system has at most one, at most. So it can be no solution or has one solution. Okay, let's see the proof. Okay, first case, if AX equal to B for B in Rm is inconsistent, then there is no solution. That's fine. Okay, so if for some B the linear system is inconsistent, then there's no solution, of course. But if AX equal to B for B in Rm is consistent, right? So if it's consistent, then right? Means that it can be solved. Then we multiply the linear system by C from left. Okay, by C from left. So this is implies us, and CA is the identity. So this implies that the solution should be equal to CB. Okay, so which shows that this consistent linear system has a unique solution. Means one solution only. Okay. Right, so this is the implication for a matrix to have a left inverse. Okay, now the next theorem, 3.2.a, give us a necessary and sufficient condition for a rectangular matrix to have a left inverse. So, and M times N matrix A has a left inverse. Okay. C, which is N times M. CA equal to identity if and only if the microphone, I don't know, the microphone is not sensitive enough. Anyway, so if and only if the kernel of A is trivial. Okay, so this is necessary and sufficient condition is very simple. That if we know that the kernel of A is trivial, then the matrix A has the left inverse. So let's go in to see the forward direction. So suppose that matrix A has a left inverse. Now, okay, so since any homogeneous okay, so since AX equals 0 is consistent, and the matrix A has a left inverse. AX equal to 0 has a unique solution. All right, and this unique solution must be, which must be the zero vector by theorem 3.2.1. Okay, because that the theorem says that if a matrix A, the coefficient matrix A has left inverse, then any such linear system has at most one solution. But because this homogeneous linear system has at least one solution already, right? Which is 0. So that this solution must be unique. So therefore, the kernel of A is just the set of all solutions for the homogeneous linear system. So this is easy. Okay, the forward part is easy. Now the backward part. The backward part says that that the kernel of A is trivial, and we want to show that A has an inverse. Okay, so now to find, so we want to find a left inverse of A. Okay, so we want to find the left inverse of A, i.e., we want to find an n times m matrix C such that CA is equal to the identity. Okay, but this requirement, when we take the transpose, will be the same. Okay, so you can take the transpose, and which is equal to A transpose C transpose equal to times M. Okay, so okay, and this is saying that all right. So we want to find left matrix satisfy this one. If and only if that we find the matrix C such that A transpose C transpose is equal to the identity matrix. So if only if A T X, all right, has a solution where X okay, where is the unknown, M times N matrix. Okay, so we want to solve such a matrix equation that A transpose T. So A transpose T as the coefficient matrix, and X is the unknown M times N matrix. And this is equivalent to AT right? So maybe I write in the next. So if and only if that has a solution, where x1 they are M times 1 unknown vectors for all and E1, E2 up to standard unit vectors in Rn. Okay, so we have to find the solution. Okay, so that means that AT xi equal to EI has a solution for each I. Okay. Okay. So we have n linear systems, and for each linear system, we should have a solution. Okay. Any questions up to now? Because our goal is to find the left inverse, right, of A. And that means that we should find a matrix C multiplied with A equal to the identity matrix here. Okay. And we just, because A is known, C unknown, right? So we just take the transpose, right? So that becomes to, so the A transpose becomes to the coefficient matrix, okay, of a matrix equation. And X is an unknown M times N matrices. So it has N columns. And each column is an M-dimensional unknown vector. Okay. So it's just like here, and we have to solve. So we have n linear systems. Okay, they share the same coefficient matrix A transpose. Questions? No questions. Good. Okay. All right. So now we know the kernel. So since kernel of A is trivial, okay? The homogeneous linear system AX equal to 0, okay, which is okay. So the homogeneous linear system actually is just a linear relation, right, of the n columns of A, right? Has a unique solution 0. Okay, so the only solution means that if we have a linear relation, then all the coefficients should be 0. So that means that the columns of A is a linearly independent set. Okay. Actually, we have a theorem before, so but I just stated it explicitly. Okay, so then the set of n rows A1 transpose, A2 transpose up to AN transpose of A transpose. So columns of A becomes to rows when take the transpose of A transpose. So this rows is linearly independent too, right? And the reduced row echelon form U of A transpose has no zero row. Right? Has no zero row by theorem 1.3.11. Okay. So in chapter 1 we have shown that actually the theorem 1.3.11 says that if the rows of a matrix form a linearly dependent set. So if the rows of a matrix are linearly dependent, then there is a zero row, right, in any row echelon form of A. Not necessarily reduce any row echelon form of A. We prove that, right? So the contrapositive statement will be that that if the rows of a matrix form a linearly independent set, then any row echelon form of the matrix A has no zero rows. If it has no zero rows, it means that every row has a pivot. Right? Remember that? So thus every row of U has a pivot. Okay? So U is the row echelon form. So every row of U has a pivot. Now A transpose E I is not equivalent to the U and the UI. Okay, so by row operations, when we want to solve this linear system, okay, the associated augmented matrix, right, by reduction or by elementary row operation, goes to U and UI for here. Which must be consistent. Why? Because every row of U is not a zero rows. Okay, so that it must be consistent. Okay, so there is a solution. Okay, xi is equal to ui. So the ui is here. Okay, I think I use the same symbol. It's not a good practice. So please, okay, UI. So I should use not UI, I should use VI. Okay, so it's V, not U. Okay, so I think I have a typo here. Okay, so please do the correction. Okay, it's not UI because that the solution may not be equal to this UI, may be different. Okay? Right. This is because the U may not be identity matrix. Okay. So, but actually, it's because this is consistent, so that it has a solution. We call it VI. But oh, I have a lot of to correct. Maybe I select two. Instead of correct this one, I put tilde here. Okay. Maybe it's much more easier. So you put U tilde. U tilde is different from UI. Okay. All right. So otherwise, I will need to rewrite a lot of things. Okay. So here. Sorry. Okay. So just change this one. Okay. So there is a solution. Okay. And then All right. So, all right, and then we have A transpose U1, U2 up to UN equal to E1, E2 up to En. Okay, so we find U1, U2, and UN. Okay, so there exists a solution there. All right, and so we have TU. We call D here equal to identity where D is defined to be U1, U2 up to UN. Okay. All right, and D at M times M matrix. All right, so now we take the transpose again. So this says that DTA equal to the identity. Okay. Okay, so with C to be DT, so we have a left inverse to a left inverse of A. And then we have done. Okay. So that is the end of the proof. Okay. Any questions? So all the materials needed here about solving linear systems. Just as I promised you at the beginning of the semester, that even though we dig into very deep properties of linear algebra, we still can link back to solving linear systems. Okay, all the techniques we learned in chapter 1 will be used repeatedly, again and again and again. Okay. Questions? All right, so they are about left inverse. All right, consider a linear system. AX equal to B. Okay, if A has a right inverse, if A has a right inverse B, then this linear system has at least one solution, which is B multiplied with B. So you can compare the statement of this theorem from the statement in theorem 3.2.1, there, if we have a left inverse, then any linear systems with the matrix A as the coefficient matrix has at the most one solution. But on the contrary, if the matrix A, the coefficient matrix A, has a right inverse, then this linear system has at least one solution. May have more and more. Okay, so this is quite different. We can compare them, right? Compare them. The proof is quite easy. All right, so we just check, right? Because it already gives you a solution here, right? So just plug in the solution. So x is b, right? So with the unknown vector to be this vector, so we check. Okay, we just check by substitution, and this by also the activity of matrix multiplication. We have this one, and because B is a right inverse of A, so this is the identity matrix of B, and so this is B already, and we have done. Okay, so it's quite easy to see that once the coefficient matrix has the right inverse, then the corresponding linear system for any B, right, has at least one solution. So it is not surprise to have the following supplemental theorem, the 3.2.b, and M times M matrix A has a right inverse if and only if the columns of A, the column space of A is equal to Rm. Okay. Why? Because all right, so the proof, so the 4 pi is quite simple. So let B in Rm. Since A has a right inverse, okay, so the linear system Ax equal to B, okay, has a solution. Okay, by the previous theorem. Okay, the previous theorem tells us that we have a solution, and we call this solution as U. So U1, U2 up to UN are components in this vector U. So then AU equal to B. This is saying that A1, A2 up to AN, U1, U2 up to equal to B. So this is saying that B can be written as a linear combination of the columns of A. So this is saying that B is in the span. The span of the columns is just saying that it's column space of A. Alright, so for every vector in Rm, this vector must be in the column space A, so that this shows that Rm is a subspace of column space A, right? But as we know, the column space of A must be a subspace of Rm. So the conclusion is that column space of A must be equal to the m-dimensional Euclidean space. Okay, so the forward part is down here. Okay. Now we look at the backward part. Right, now we have assumed that the Euclidean vector space Rm is equal to the column space of A, so that each standard unit vector EI, I from 1 to m in Rm is in the column space of A. And then there exist scalars, say bi1, bi2 up to bin, bin, such that E I can be written as a linear combination of the columns of A. Okay? For all. Right. So every standard unit vector EI in Rm is a linear combination of the columns of A, because that is in the column space. Alright, so we let Bi to be a column vector, right? Which put all the coefficients together. Then we can rewrite that A, B1, B2, up to Bm is equal to B1, B2, up to Bm. Okay. Okay. So this is actually A. Maybe I will write them. This is A1. So this is A, Bi. right? So ABI is equal to EI, right? So we put them together. So A B1 B2 BM equal to E1 E2 EM here. And this one is the identity M times M. Okay. And so this is AB, and A is M times N, and B is N times M, where B is defined to be B1, B2 up to Bm. Okay, so now we construct a matrix B. So B is a right inverse of A, and we have done. Okay. So now we have construct a right inverse of A. Okay. And the B, all the entry of B is from here, that the information that column space of A is equal to Rm give us this linear combination. Okay. All right. So this is supplementary matrix theorem give us a clear, necessary, sufficient condition for a matrix to have a right inverse. Okay. Okay. So let's take a short break now. 声音没有办法。
123，123。
要非常靠近。Hello。Hello，OK。那边的问题。
不好意思啊。
OK，great，thank you。Okay. Yeah. Yeah. Very good. Thank you. Okay. Okay. Yeah. It's nice. Okay. Great. Thank you. 谢谢哈。Right. So the above discussions about general rectangular matrices. Okay. Now we go specific to square matrices. So we recall that an n times n matrix A is invertible if there is an n times n matrix B such that AB equal to BA equal to the identity matrix. And we know such a matrix is called an inverse of A. And we have shown, right, in lemma 1.2.a in chapter 1 that if an n times n matrix A has an inverse, okay, then there exists one and only one such inverse. And we also denote this unique inverse as A inverse here. Okay, so that has been done in chapter 1. Also, since A inverse A equal to A inverse equal to identity, so A inverse is also invertible. So this A inverse matrix A minus 1 is also invertible, okay, and its inverse is A, i.e. we have A minus A inverse goes to A here. Now, from either here or there, we know that the inverse of an invertible matrix n times n matrix. Okay? So the inverse of an invertible n times n matrix, say like here, B, right? B is the inverse of invertible matrix A here. So B is the right inverse of A, and B is also left inverse of A. You can see. So you can see that. So the inverse of A is both a left inverse and a right inverse of A. Okay. And finally, an invertible n times n matrix is also called non-singular. And a non-invertible n times n matrix is called singular. Okay, so that are terminologies. So there is a question. Now for an n times n matrix A, is it possible that there are two n times n matrices B and C such that AB equal to, so B is a right inverse of A, C is a left inverse of A, and B not equal to C. So we ask such a question. So for a square matrix A, we will ask for the possibility to have two different matrices, B and C, such as B is a right inverse of A, and C is the left inverse of A. All right, so to answer this question, we will look at the following theorem, 3.2.4. If A and C are n times n matrices, so they are square matrices of the same dimension, such that CA is equal to the identity. Okay. Suppose A and C are squared, square matrices, and have this identity. Then we have AC equal to the identity. Okay. So this is non-trivial, right? It's non-trivial. All right, so let's give a proof of the theorem. All right, so since CA equal to the identity, C is a left inverse, okay, of A, and we have the kernel of A is trivial. Okay, that is theorem 3.2.a, that a matrix has a left inverse if and only if the kernel of A is trivial. Okay, so this is by theorem 3.2.a. All right, and now, because the kernel of A is trivial, each column of each column of the reduced row echelon form U of A has a pivot. Because if a column of the reduced row echelon form U has no pivot, then the corresponding unknown variable can be set to be free. Okay, if we can set a variable to be free, then the kernel of A cannot be trivial. They have a non-trivial solution there. So each column has a pivot, right? Each column has a pivot. And the number of rows is the same as the number of columns, so that every row has a pivot. Because if every column has a pivot, then the rank of the matrix is n, so that every row has a pivot. Okay. So the only choice is that so that U should be equal to the identity. Okay. And so we have A. Okay, so A is row equivalent to the identity matrix. All right, so now consider simultaneously solving nonlinear systems in the following way: AX equal to identity. This is just saying that, so this is n times n. So the unknown matrix X here is just like a okay, so this metric equation contains nonlinear systems here. Okay, we can nonlinear systems. Okay, so So the associated augmented matrix becomes to A, I. Okay, so by elementary law operation, this becomes to okay, so it goes there, and which is consistent, of course, right? Because the the reduced version form has no zeros. So that's the X matrix is a solution. All right, so it's A W equal to I n times n. Okay. Now, okay, so we find a right inverse, right? So W becomes to a right inverse of A. Now, so now we want to find, so AC is ACI, it's AC and the AW. Okay, because AW is identity. And also we have ACA W. And it's A, but because C is a left inverse of A, so this is identity. And this is AW. And AW is identity. And we have done. So AC is identity too. All right, so the theorem has a significant consequence that you see that if a matrix A has a left inverse, so here A is a square matrix. So if a square matrix A has a left inverse, this left inverse must be a right inverse of A, okay? And so C becomes to an inverse by here. Okay, so C satisfies this. So C is an inverse of A, and because inverse of A is unique, so that C is just the inverse of A. All right, so remark. So by theorem 3.2.4, if an n times n square matrix A, right? So if we have an n times n matrix A has a left inverse C, then it is invertible, and the inverse is C itself. On the other hand, okay, on the other hand, if A has a right inverse B, all right? So if A has a right inverse B, then then A is a left inverse of B, right? Because they are equivalent, as I said at the beginning of today's lecture, that if A has a right inverse, so means B is a right inverse of A. This is same as saying that A is a left inverse of B, right? So A is the left inverse of B, and then A is the inverse of B. So then B is invertible, and its inverse is A. Okay? By the theorem here. Thus, A is invertible. And its inverse is B. Okay. So again, so if A has a right inverse B, then A is invertible and its inverse is B. All right, any questions at this moment? Okay, so the following theorems are just consequences of what we have up to now. So for an n times n matrix A, if AB equal to AC equal to the identity. So if A and B are right inverses of A, then A and B and C are inverse of A. But inverse is unique, so B must be equal to C. All right, so for symmetry, I just write down a corollary. If CA is equal to BA, so if B and C are left inverses of A, then C and B are inverses of A and must be equal. Now for an n times n matrix A, if CA equal to identity and AB equal to the identity. All right, this is our question raised here. Suppose we have B and C such as B is the right inverse of A and C is the left inverse of B, and we ask if that can we have the situation that B not equal to C? And the answer is no, because if C A identity, then this C must be the inverse of A. Also, this B must also must be the inverse of B. So the only choice is B equal to C. All right, so the answer to that question is no. Okay. It's no. All right. If two is for the record, right? If two matrices A and B are invertible, then AB, the product of A and B is also invertible. And its inverse, the inverse of A times B is B inverse multiplied with A inverse. We proved that before, so this is just lemma 1.24D. We mentioned in chapter 1. Okay, so the last theorem of chapter 3 is here. This theorem is called invertible matrix theorem. Okay, for an n times n matrix A. Okay, so A is a square matrix. The following 16 statements are equivalent. Okay, so we have 16 statements. All right, and they are equivalent to each other. 16. Take, I think, at least 5 minutes to write it all. Okay, so A is invertible. Right, the first statement is that A is invertible. This statement is equivalent to say that A has a right inverse. Okay? So A has a right inverse. But A has a right inverse if and only if the column space of A is just equal to the n-dimensional Euclidean space. And if the column space of A is equal to the n-dimensional vector space, then for each B in Rn, the linear system Ax equal to B has a solution. Right, so these four are equivalent to each other. The fifth one say that A has a left inverse. Okay, A has a left inverse. But when A has a left inverse, if and only if the kernel of A is trivial. Okay. Okay, and if the kernel of A is trivial, then to solve the homogeneous linear system, every column of A, I have a typo because I put a S there. So please delete the S. Okay, so please delete S. So every column of A has a pivot position. Because if a column of A has no pivot position, then the corresponding unknown variable can be set to be free. Okay, and so then the kernel of A cannot be trivial. Now every column of A has a pivot position, so that means that the rank of A is equal to the size of the matrix, which is n. Okay, and when the rank is n, so every row has a pivot. So A is row equivalent to the identity matrix. This is 9. Okay, and the 10th, every row of A has a pivot position. All right, so it's symmetric to 7, right? Every column of A has a pivot position. It's equivalent to every row of A has a pivot position. 11, A transpose is invertible. Okay, A transpose is invertible. And I will give an explicit proof for that. 12, the set of all columns of A is linearly independent. So the corresponding statement would be the set of all rows of A is linearly independent. Okay, 13. Okay, we have 3 more. All right, so 3 more. Yeah. (14) The linear transformation T, right, from X to AX. Remember, every n by n matrix corresponding to a linear transformation from Rn to Rn, okay, by this, right? And the linear transformation is injective, means 1-to-1. 15, the linear transformation T from X to X is suggestive. Onto 16. The linear transformation is bijective. Okay, so now we have done 16 statements. They are equivalent to each other. In particular, for the last three, you can see to show that a linear transformation, right, defined by a square. Remember, this is a square matrix A is bijective if and only if that it is injective. So you just show that this linear transform is injective. Then you can conclude that you don't need to show the onto, right? Then you can conclude that this linear transformation must be bijective, right? The important thing is that A is a square. If A is not square, then the statement, they are not equal to each other, okay? They are not equivalent to each other. So it's very important to know we are talking about a square matrix. So this is square. Okay, and the proof. Well, so actually 1, 2, and 3, and 4, they are equivalent, and 10 and 13, they are equivalent. The reason here is that this is from theorem 3.2.4. Okay, this is just we just proved. Okay, of course, if A is invertible, then it implies a lot of other things. But in theorem 3.2.4, if A has a right inverse, then A is invertible. Right? We just proved that. So this is the theorem by theorem 3.2.4, and 2 is equivalent 3 is because of theorem 3.2.b. So maybe I save the space saying that theorem 3.2.4. This is theorem 3.2.b. And 3 is equal to 4, equivalent to 4. This one. Okay, and this can be seen in a theorem in chapter 1, which is theorem 1.2.3. And 4 equivalent to 10. Every law of A has a pivot position. So this is a theorem 1.2.4. Okay. And 13 is theorem 1.3.11. Okay. About the rows must be linearly independent. So 1, 2, 3, 4, 10, 13, they are equivalent to each other. All right, so this is the one line. The second long line, well, I can give a short line. Then 3 is equivalent to 15. 15 is saying that this linear transformation is surjective, but it's surjective if and only if the column space of A is Rn. It's just so the range is equal to the codomain. Okay, so this is from theorem 2.3.4. Okay. So it's a review, right? Because this theorem related to a lot of results in the first 3 chapters. So it's a very good as a summary of the first 3 chapters. Okay. So if you can comprehend this invertible matrix theorem, then you can grasp the idea needed in the first midterm. Okay. All right. So 1 is equivalent to 5, equivalent to 6, equivalent to 12, and 7. Okay. So this is from theorem. 3.2.4. Okay. The fifth one has a left inverse. So this is theorem 3.2.4. And 5 is equivalent to 6. They are equivalent to each other. This is from theorem 3.2.8. Okay. And 6 equivalent to 12. 6 says that kernel of A is trivial, and 12 is that the set of columns of A is linearly independent. So this is from lemma 1.3.8 in chapter 1. All right, and the last one, 7th, every column of A has a pivot position. Okay, so this is from theorem 1.3.13. And 6 is equivalent to 14. 6 here, kernel of A is trivial. And then the corresponding linear transformation is injective. Okay, so we have that by theorem in chapter 2, theorem 2.3.5. Okay, and 7, 8, 9, 10. Right, so this follow from the definition of the rank of a matrix. And the structure of a reduced row echelon form. Okay, because reduced echelon form is take the echelon form, the stairwise form. Okay. So 7, 8, 9, 10 give you a particular one. So we divide it into 2 parts. 1 imply 11. Okay, so we want to show that if A is invertible, then A transpose is also invertible. Okay. Now, since A is invertible, so that we have this one. Okay, and by taking transpose, we have A inverse transpose equal to A inverse A transpose equal to identity transpose. Okay. So this gives us A inverse transpose A transpose equal to A transpose A inverse transpose. By theorem, 3.1 we prove on Wednesday. 5, okay? 3.1.5. Okay, and from here you see that so this matrix is the inverse of A transpose, i.e. the inverse of A transpose is equal to the transpose of the inverse of A. Okay. Okay, so that A transpose is invertible. Okay. Okay, and finally, 11 implies 1. So this follows from the fact. This follows from the fact the transpose of A is equal to A. And we just prove this one. Okay, because if one implied theorem says that if A is invertible, then A transpose is invertible. Okay? Now, so it says that this says A is invertible implies A transpose is invertible. Now, we replace A by A transpose. So A transpose is invertible implies the transpose of A transpose is invertible. Right? This is just the 1 implies 11. But A transpose, and you take transpose again, is equal to A. So we have done. Right? So this is saying that because A transpose take transpose back to A, and we have that. Okay, so the last one, 1 implies 16. All right, so this follows from 1 implies 3 plus 6, right? And okay, I think I have 2 minutes left. Anyway, so 1 implies 3 and 6. 1 implies 3 and 1 implies 6. And 3 implies 14. 3 implies 15, okay? 3 implies 15. And 6 implies 14. So 3 plus 6 implies 14 plus 15. But 14 plus 15 implies 16. So if the transformation is injective and surjective, then it's bijective. Now 16 implies 1. That is easy. So this is follow from 16 implies 14, of course. Implies 6 implies 1. And we have done. Okay. All right, so we prove the equivalence among the 16 statements. Okay. So they are equivalent to each other. Any questions? Okay. So no questions. So that is the end of chapter 3. And our first midterm will cover the first 3 chapters. Okay. And it will be held on November 3rd. All right. So that's it. And I'll see you next week.